He's going to be telling us about Hook formulas for skew shapes.
Do you hear me online? Yeah. Okay, thank you very much. It's a pleasure to be here. It's my first time in Waterloo. It's a pleasure also to meet Professor Golden and Professor Jackson in person for the first time. So today's talk is going to be about both combinatorial and algebraic enumeration of certain objects, and is going to use a very fine result of Ian Golden and Angela Foley. So hopefully it is appropriate for this conference. So what is this about? So I do algebraic combinatorics. So we count in algebraic combinatorics, we like to count standard Young tableau. So they come from representation theory and so on, but they're perfectly fine as combinatorial objects. They're linear extensions of partially ordered sets of certain type and so on. So they are indexed by partitions lambda. So yesterday we saw a lot of partitions, and the partition lambda is drawn as a Young diagram, and we enter the numbers from 1 up to n. In this case, it's going to be from 1 up to 5, so that they are strictly increasing along rows and down columns, and each of the numbers appears exactly once. So here, in this example, are the 5 possible standard Young tableau that you can get. So now, being combinatorialists, we would like to know how many of these objects are there. And in this case, we have a beautiful formula, the Hook length formula of Frame, Robinson, and Troll, that tells us that the number of standard Young tableau of shape lambda, this f lambda. So this f lambda is standard notation that I'll be dragging around. So if you see that again, that means we're counting standard Young tableau, is equal to n factorial divided by the product of the hook lengths. And the hook lengths are this. So the hooks of a tableau at a box is exactly what's drawn here. The boxes to the left, to the right in the same row and below it. And we count how many of these boxes we have. So in this particular example, the hook length is 5, so all the blue boxes. And for this particular case, we apply the formula. These are all the hook lengths we get. We get the number 5 in the end. All right. So I think everybody here knows this, but I have to review just in case. So what's the next step? The next step, of course, is that we do skew standard Young tableau and also semi-standard Young tableau. So what is the skewing procedure? We just take a partition lambda and we remove from it a partition of shape mu. So this is lambda over mu. We bite it off from this corner, and we still have a bunch of boxes to fill it with numbers. And again, we use the same rules, strictly increasing along rows and down columns. Each number appears exactly once. This is for the skew standard Young tableau. And the skew semi-standard Young tableau, which are the building blocks of the Schur functions that will show up later on and so on, is when the numbers can repeat, but they should be strictly decreasing down rows and weakly increasing along, strictly decreasing down columns and weakly increasing along rows. And what kind of formulas do we have? Well, for the number of standard Young tableau, this is a corollary of the Jacobi-Trudi identity, is that the number of skew standard Young tableau of shape lambda over mu can be computed as a certain determinant, which from computational complexity point of view, since having the audience, is actually a nice formula, but on the other hand, for asymptotic applications or any others is not so useful. Another one comes from the Littlewood-Richardson coefficients, but then the problem here is that Littlewood-Richardson coefficients are difficult to compute. And just to settle all hopes down for a product formula, this is a special case of this skew counting the skew standard Young tableau. We have this zigzag permutations actually. which are counted by the Euler numbers, and they have this exponential generating function, so the numbers are pretty complicated in this case. All right, so now, so what can we do? So here is another formula, relatively recent, which was presented by Hiroshi Naruse at the SLC conference, and it says that the standard Young tableau, the number of standard Young tableau of shape lambda over mu is equal to n factorial, the number of boxes, times the sum over something called excited diagrams. And for each of these excited diagrams, we take the product of the hook lengths, as in here. So this is like an interpolation of a hook length formula. And what are these excited diagrams? So they are defined algorithmically. So they are obtained by shifting boxes along the diagonal as long as we can. So the blue boxes are the boxes of mu, the partition which we are removing. We can do this move. So we can shift it down the diagonal as long as we don't have any other blue box obstructing the motion. And so, for example, we can take this shape. We can shift these three boxes down. So we first shift the corner ones, then the other one here. We will get this excited diagram. And then here are the hook lengths. So the hook lengths are considered inside the entire partition lambda. So the distances to the border of lambda. Right. So, for example, this 6 goes, so the 6 represents the hook length of this square, and this is what comes into this type of product. So this would be the contribution to one of these summands. All right. Any questions? And here is a full example for the zigzag permutations, actually. So that they correspond to this staircase shapes. These are all possible excited diagrams we can get, and this is what we get from this formula when we expand it. For each of these excited diagrams, we have a term with these products, and if we do the math, in the end we get 61, which is the Euler. Okay, so the question is, how do we actually prove this? Because when we saw this, there was no proof, and how do we actually generalize it? So here are the two answers. So one way to generalize standard Young tableau is if we put in a Q and we evaluate a Schur function. So this basically the generating functions for semi-standard Young tableau of shape lambda over mu, Q to the volume, or the sum of the entries inside this semi-standard Young tableau, and it is equal exactly to the sum of these excited diagrams, and we have the products of the Q analogs of the hook lengths here. So here is an example how this looks like. So for this Q Schur function, we will have five of these terms. These are the sum of them. And we can also do reverse plane partition. So this is a different type of generalization. Skew reverse plane partitions. The difference between reverse plane partitions and semi-standard Young tableau is that we don't have the strict restriction on the column. So we have weakly increasing columns and weakly increasing rows. And then this set is a little bit larger of things that we sum over, and I'm going to explain this later in a moment what this means. What are these PD with pleasant diagrams? But before that, let me tell you a few applications of this result. So why is something like that useful? One thing is we can actually do asymptotics. So if we have some limit shapes for lambda and mu, like in these examples, we have something specific, then we can expand we can see how it grows as a function of n when the shapes are expanding in both directions. So certainly the leading term would come out as square root of n factorial, which is 1/2 n log n, and then the next terms, of course, would be we will get bounds for the next terms this way. We can. This is a little bit of a stretch of what exactly the connection is, but there are some special types of Schubert polynomials which come from algebraic geometry, but one can also think of them as configurations of this type, so like statistical mechanics objects. And we want to count how many there are asymptotically, so this is still an open problem in generality, but one can try to do something with the formulas that we'll get. We can also get explicit product formulas for certain shapes, for certain skew shapes. So here are a few examples of classes of shapes for which there is a product formula, even though it's not a straight shape, and it can be proven with this Narusse-Hook length formula. One can do weighted lozenge tilings. So again, this is a statistical mechanics object, dimer covers of the hexagonal grid. If you let the mesh size go to infinity, we want to know how this thing looks like in general. And actually the volume of this thing is exactly proportional to the number of standard Young tableaux of certain skew shape. And most recently, we use this formula to figure out this conjecture here. So this is a conjecture for general posets, but we can try to do it for Young diagrams since we have a formula. So if we take two elements, the conjecture is that we can find two elements in the poset, so such that the probability that one is smaller than the other in a linear extension or in a total order, or the values of these cells in a standard Young tableau, if you like, minus the probability the other way, that these probabilities are very close to 1/2, or in other words, their difference goes to 0. So one can use this formula to do that type of asymptotics. Okay, so now if there are no questions, I want to show you how to prove this formula, and in particular, use one identity. So here is an example from that paper that we are going to use from 95. Planar decompositions of Tableaux and sure function determinant. So this is a great generalization of Jacobi-Trudi, Jambelli identity, and so on. And what is the statement that we are going to use? So here is a particular planar decomposition of Young tableau, and I think that my clicker ran out of battery, so I cannot really show you what to look at. Yeah, okay. Oh yeah, I'll use the buttons. Okay. Okay, thank you. That was nice. So there is so we can take a skew shape, we can decompose it into border strips or like single skew tableaux of width exactly 1. So just following a lattice path. And if it almost doesn't matter how exactly we decompose it, but the point is that this strip should end on the borders of the Young tableau, and then one can form a determinant where each entry is just a border strip, a single border strip sure function, when the border strip is determined from the profile of bigger or the smaller partition, it's depending which convention you would want to choose, and the endpoints are determined by the combination of the two endpoints for theta I and theta j. So there are certain rules one can do that. So how do we apply this in our case? Yeah, but the controls are not working actually. Now it's working. So the first thing is we need to figure out what to do with a border strip Schur function. And a border strip Schur function can be expressed as a sum over all possible lattice paths between the endpoints of the border strip which lie inside lambda. So all border strips here, which are themselves skew shapes, and for each one of them, we take the weight is given by 1 over 1 minus q to the hook length of the particular box. So we do a product over all boxes inside this lattice path or border strip Schur function. Sure. Thank you. Yeah. Okay. So here is again one example. So this is this time I actually inverted the color. So this is the border strip is the blue one, and here are all possible border strips within our shape lambda that we get, and the weights for each one of them. And then there is another step, which is to interpret the excited diagrams or the complements of the excited diagrams as non-intersecting lattice paths inside lambda. And the recipe is the following. So we cut our skew shape greedily, starting from the inside. This would be the endpoints of the lattice paths. And you can see that every time I push a box, this is like taking an inner corner of a lattice path and turning it to an outer corner. So we can follow this procedure, and you can see that all these excited diagrams are just complements of this non-intersecting lattice paths which cut our Young diagram. And now we can put the two things together. So we use the special case of the Lascaux-Pragatz identity, but this is generalized. This is what paper Hamel-Goulden actually generalized. So here is the special case of the Hamel-Goulden identity. And we write the skew Schur function as a determinant of these ribbon-shaped Schur functions. Then we insert these formulas for the border strips. So we actually have a determinant. What are the entries in the determinant? Lattice paths with endpoints AI, BI, CJ, DJ. So this would be the endpoint, the starting points of one border strip and the ending points of the other. And so the constraint is that they are in lambda, and then we have this product of weights for each box in the lattice path. So it's a local formula. And then we use our favorite Lindstrom-Gessel-Viennot determinantal identity for counting the number of non-intersecting lattice paths from a determinant. So it basically tells us that when we expand this determinant, we'll cancel out everything except the tuples of paths which are non-intersecting. So NILP means non-intersecting lattice paths here. So we'll have these non-intersecting lattice paths. And then the last step is just this interpretation of the excited diagrams and this non-intersecting lattice paths and reformulating this identity. Okay, so, all right. So this is one proof, probably my favorite proof of this result. So there are some other half proofs, I would say. So in this case, so one can also do a bijection. So there is a bijection which explains this identity. What is the bijection? Actually, the bijection we already know. It's the Hilman-Grassi correspondence, which you can find in chapter 7 of Enumerating Combinatorics, volume 2. And it's an algorithmic bijection which starts with a reverse plane partition, like in this case. So the entries in the boxes are weakly increasing along rows and down columns. And there is a certain procedure which moves left to right and top to bottom, and cuts off as much as possible from this reverse plane partition. And so it cuts off various border strips, and whenever it cuts a border strip, it records in this array in the bottom the endpoints in the box, which gives the coordinates of the endpoints of the border strip. We add a number 1. So this is like a counter which we increment every time. So here this border strip went all the way from the bottom till the end. So this is the corresponding corner box, which is going to record a 1 in here, and so on and so forth, until we get to the 0 reverse plane partition, and we fill out an array of numbers which have a priori no restriction between each other. And then the weight of the plane partition, so the sum of the entries, is exactly the weighted sum of entries in the array, weighted by the Hook length of the particular boxes, and the Hook length is just the length of this border strip that we just removed. So this is so the weight of the plane partition is related directly to the weight of our array, and this is basically how you can actually prove in a combinatorial also the Hook length formula, the original one, because this turns into a generating function. So if Q2 the sum of the entries in the plane partition following this procedure, it's just summing over all arrays, and for each entry of the array this weight, and since the entries in the array are independent, this factors into a product and we get this. And then so the difficult part here is to figure out what happens if you restrict our bijection, our Hilman-Grassi bijection, to a skew semi-standard Young tableau. So first there is the skew shape. So we're forcing that these entries in mu are all 0. And second, we have the strict increase, and the strict increase actually is really the hard part, and why this is only half a bijection, because I mean, we can prove that it's a complete bijection just by knowing that the identity holds from for the other reasons that I showed earlier. But a purely bijective proof in both directions we don't really have yet. So the bijection basically tells us that the skew semi-standard Young tableau used under the Hilman-Grassi map correspond to exactly the excited diagrams. So we call them excited arrays because we are taking an excited diagram from this one to turn it into this one, and we look at all possible fillings of the non-blue boxes with numbers, with one restriction, that these entries along this broken diagonals here, which are obtained using the procedure in some well-defined fashion, then these entries are non-zero. So we do have, there is an actual bijection of what each of these entries in the sum actually means. But the nice part about this Hilman-Grassi bijection is that actually it gives us directly the combinatorial identity for the reverse plane partitions. And just to open up a bracket here, so for reverse plane partitions of skew shape, they no longer can be enumerated via Schur functions or anything like that, because whatever generating function, multivariate generating function you want to assign, it's not going to be actually symmetric. You can play around with it. So these techniques wouldn't really work. So we need to do something else. And this is what we obtained just using the Hilman-Grassi correspondence. So this is the excited diagram. We create these pleasant diagrams. So not that exciting, so we take any subset of boxes of the white boxes here. There is one restriction that we need to actually have the boxes in the corners also. And then summing over all reverse plane partitions, actually using the Hilman-Grassi correspondence, we get that all the arrays in the Hilman-Grassi correspondence would be fillings of this type of diagram. So the red boxes or magenta boxes here in this diagram, and we will fill we sum over all these types of fillings, and for each one of them we have this product formula. So this would be the non-zero entries really of our array. And this is only proved by this bijection. And so for the sake of time, and of course, so how do you get the counting formula? Well, you let Q go to 1 in a certain way. So we either from the theory of P partitions, or we use the notions of order polytopes, so that the number of linear extensions or the number of standard Young tableaux is actually the volume of the normalized volume of the order polytope. So we can take Q to the 1 limit after we multiply by 1 minus Q to some 1 minus Q, the Q analog of n factorial in some sense. We can get the actual formula for the number of standard Young tableaux of this shape. So how else can we prove this? And this is actually originally where this came from. There is an algebraic proof. It comes from a bunch of formulas and combination of them for localization formula of Schubert class indexed by a permutation, localized at another permutation V. What this means for us, let's treat it as a black box, but basically there is a way to associate two Young diagrams permutations by tracing out the paths. So here are the two examples. The inner and outer path correspond to the W and the V permutation. And if you trace them out, so first the horizontal steps, then the vertical steps, you'll get a permutation with a single descent. This is called the Grassmannian permutation. So there is a one-to-one correspondence between these permutations and the shapes. And for these types of permutations, there is this formula, and these are exactly these excited diagrams here, and these are just formal variables in this case. And the other thing that we're gonna need is this generalization of Schur functions, this factorial Schur functions. So they're still symmetric in the x variables, but there are also these parameters A. So this is a formula, determinantal formula. And a result from algebraic geometry basically tells us that the localization formula can be computed as a certain evaluation of a factorial Schur function. And if you plug in both sides with various letters and you do some transformations, then you will actually get to the skew Schur function using this complicated the results from algebraic geometry. Okay, so I just put it on the slides for the record, but don't look at it. It's to here. So I just want to tell you a little bit of newer results since what I was saying was done like between 2015 and 2018 mostly, but recently Recently, we did another application and a generalization in some sense of these formulas, and they pertain to this combinatorial model. So this comes from K theory, but combinatorially we're looking at what's called increasing tableau. So increasing tableau are tableau where we enter the numbers 1, 2, 3, and so on, maybe with repetition, but we require that they're strictly increasing along rows and down columns. So here is an example of an increasing tableau, and so this is this is not actually standard naming. So we called it standard increasing tableau, but I think that Oliver probably will object to that and say something else if he's here now. But so what we call standard increasing tableau would be such increasing tableau where the consecutive numbers show up. So all consecutive numbers from 1 up to some number, each of them will show up at least once. So there is no skipping of a number here. So 1, 2, 3, 4 is here, 5, and we stop. So this one is not actually standard because it's missing 4 and 5, for example, and 7. And so here is some notation. So M of t means is the maximal entry of this increasing tableau, and this square bracket t less than k basically just is the Young diagram corresponding to all entries in this tableau which are strictly smaller than k, and the analogous notation greater than or equal to k, and so on and so forth. So here is an example. So the entries smaller than 4 in this tableau are this shape. So here is a hairy formula. So this we call the KHLF. K comes from K theory. So this is a standard increasing tableau of shape lambda. For each one of them, we have some weighted sum depending on the entries in this tableau. On the other end, we have a product formula with the Hook lengths and some other factors. Okay, so what does this mean? So here is a more general formula with some formal variables. Again, it looks very hairy, but here is a specialization that maybe you can actually prove if you're bored. So you can try to prove this directly. So this generating function, t goes over all standard increasing tableau of shape lambda, q to the sum of the entries in this tableau. Then we have this factor 1 over 1 minus q to the number of boxes that are occupied by entries greater than or equal to k. K goes from 1 up to m to the t. So if this was a standard Young tableau, you know exactly what this is because every entry occupies exactly 1 box. Every number occupies exactly 1 box. And then on the other hand, we just have the product of Hook lengths, 1 over 1 minus q to the Hook lengths. So this one we can prove combinatorially without using all the hairy formulas. Here is an example of how it works in practice for this shape, the shape 2-1. We have something like that, and but there is actually a skew KHLF, which looks as hairy as maybe even worse. So we go over all standard increasing tableau of a skew shape, which would be defined in the same way. Again, so we have these weights, but we can put actually the formal variables here. We can specialize them to q and so on. And then we can get this expression. So when we specialize some variables to the variables y to q to the I, so we get this expression. So that one, I'm not sure this has a combinatorial proof. So this is sum over all standard increasing tableau is no longer a product of the Hook lengths like it was in the straight shape case. in this case, it is again a sum over some types of diagrams. So there are these generalized excited diagrams, which I will show in a moment. And then we have this again weighted product for the entries in these diagrams. So what are these generalized excited diagrams? So they are really so they are a superclass of the excited diagrams because we have two types of moves. Either we shift the box down the diagonal, or we shift and duplicate the box. So, or we just take another copy down the diagonal. So from this, we can either do this, or we can do this if we have no obstructions along the way. So if we take this shape, for example, this is all the generalized excited diagrams we can get using this method. So they also correspond to non-intersecting lattice paths in some sense. So this case going to be the Delanoy paths, where we allow some diagonal steps. But it's not exactly non-intersecting because this thing here is forbidden. So these are still non-intersecting, but we are not allowing this to happen. So this is not quite just non-intersecting lattice paths. So there is an extra restriction over here. And they also have to do with the flagged set value tableau, which is not a surprise given that this whole formula comes from, and this whole thing comes from the K theory. And since I'm out of time, I will just show you how the proofs go. And unfortunately, this time I cannot show you a nice combinatorial proof. So the proofs are coming from putting together various things coming from the K theory, and so which are embodied in the double Grothendieck polynomials for Grassmannian permutation. So double Grothendieck polynomials replace our factorial Schur functions in the previous proof, and so here is what we have. So there are some operations that are defined over here. The factorial Grothendieck polynomial can be defined with this type of determinantal formula. So again, so this is using these operations. So this is not the standard formula. This is so it's in some sense it is similar to the factorial Schur function, but not quite. And then one can so the K theory of the Grassmannian can be encoded with evaluations of factorial Grothendieck polynomials and certain y's which come from the diagram lambda. And so here are a few identities. So one is that one can express the structure constants in the K ring. This what they call K mu lambda lambda. So this would be like a generalization of the Littlewood-Richardson coefficients. One can express them using this generalized excited diagrams in this way. And then there is also also recursive type of formula, and this relation here means that the difference between nu and mu as Young diagrams is single boxes on different rows and columns, and this is really what giving us the standard increasing tableau. And we are expanding this as a chain of tableau which all differ by just the single boxes in given rows and columns. And that's it. Thank you.
Are there any questions for Greta?
So I recently become interested in things called cylindric standard Young tableau.
We don't, and I mean, well, I'll be curious to hear more about this. So maybe there would be something. Yeah.
Are there any other questions? And Greta, could you please repeat the question then?
Okay, so Sergi was asking about cylindric Young tableau. If there are such formulas, we don't know, but we can look at it. There may be, so it depends what's available. We don't know yet. So, but if you actually have a family of Tableaux or some symmetric functions that have interesting recursive properties, please talk to me. So there may be. I mean, that's.
Time. I think we'll then thank Greta again and.